In the previous lecture, I have discussed various tests for testing about the equality or inequality of the means or variances of two normal populations. We also saw some special cases where the normality assumption may not be valid, and therefore we may take some approximate tests. Now we will look at certain applications of these tests by various illustrations here. Suppose we want to compare the average yield of a certain crop in two different states. Now if we are looking at this, then we may have a random sample taken from the two states. So for example, you consider, so we are looking at say comparing say average yields of a certain crop in two different states. So in state 1 we considered say 10 districts say, and on the basis of the random sample we observed that the sample mean turns out to be 825 say metric tons. Similarly, in state 2 we took another random sample of 10 districts and the average yields turn out to be 815 metric tons. It is known that the sigma 1 square is equal to say 100 and sigma 2 square is equal to 60. This data is known to us. So we want to test say whether mu 1 is equal to mu 2 against say h1, mu 1 is not equal to mu 2. Now onwards I will consider this hypothesis as 1. Second hypothesis I will consider as h naught mu 1 is equal to mu 2 against h1 mu 1 is greater than mu 2, and of course this is equivalent to mu 1 less than or equal to mu 2 here. And a third one will be h naught mu 1 is equal to mu 2, which is equivalent to mu 1 greater than or equal to mu 2 against h1 say mu 1 is less than mu 2. I will refer to the hypothesis 1, 2 and 3 to these hypothesis problems. So here if the assumption that the variances are known is taken, then we will use the z variable, that is z test statistic, that was given by x bar minus y bar divided by square root sigma 1 square by m plus sigma 2 square by n. Now the values of x bar, y bar, then sigma 1 square by 10 plus sigma 2 square by 10. Now this value turns out to be simply 10 by 4, that is 2.5. If we are carrying out a test say at level say alpha is equal to 0.05, then I need to look at z of 0.025, that is equal to 1.96. Suppose I am having alpha is equal to 0.02, then I will have to see z of 0.01, that is equal to 2.32. Suppose I am saying alpha is equal to 0.2, then I will see 0.1, that is equal to 1.28. Suppose I say alpha is equal to 0.1, then I will see 0.05, that is 1.64. You can see here all of these values are smaller than this value. Therefore, at any practical level of significance, so in testing problem 1, h naught is rejected. Of course, if we take much smaller alpha, that means we may take say 0.01 or 0.001 etc., then of course this will not be rejected, but then it is not very reasonable to take such a low probability of the type 1 error, because that may reduce the power also. So, if we are considering here say H naught, say mu 1 is equal to mu 2, that means I am considering the problem say 3. If I am considering the third problem, in the third problem we will reject if z is less than or equal to minus z alpha, but this can never be true for any reasonable level of significance here, because z is a positive value here. So, we cannot reject. That means, if we go by this third framework, then we were thinking that mu 1 is greater than or equal to mu 2 cannot be rejected. On the other hand, if we look at 2, in the 2 we have to reject when z is greater than or equal to some z alpha. So, it will always be satisfied, that means it is always rejected. That means mu 1 greater than mu 2 is a strong conclusion. So, here H naught is rejected. So, here we cannot reject. So, we conclude that the average yield is higher in the state 1. Let us see this description carefully. What was our initial problem? Our initial problem is to compare the average yields in the two states, and we observe from the random sample of 10 districts each that in the first state it is 825 metric tons, in the second state it is 815 metric tons. So, from the observed values it is clear that the first is having higher average yield, but statistically is it significant? So, for that we needed some other characteristics. In this particular case the standard deviations are available, it is 10 and slightly less than 8 respectively. So, since these standard deviations are not very large, the sample size is not very large, therefore, this hypothesis of equality is actually getting rejected at any reasonable level of significance. Since this hypothesis is rejected, that means mu 1 is not equal to mu 2. Now, if mu 1 is not equal to mu 2, then we have a suspicion that mu 1 is greater than mu 2 precisely from here, because x bar is greater than y bar, and therefore, the hypothesis of mu 1 less than mu 2 can, that means in this favor we will never have a decision, and therefore, we consider the second hypothesis testing problem, that is mu 1 less than or equal to mu 2 against mu 1 greater than mu 2, and here the decision is in the favor of H 1. That means, we are rejecting H naught, and this is a strong conclusion, and that therefore, we can say that it is significantly true. That means, the average yield in the state 1 is higher significantly than the state 2. Let us take some more examples. Suppose there are two teams in a say wrestling competition, and we want to see whether the average weights of the wrestlers are same in the two teams, or one of them is having higher weights than the other one. because this is a crucial factor in the outcome of the actual match. So, we are having weights of players of the two teams. So, from team 1, 8 wrestlers are randomly selected and their average weights are 90 kg, and the standard deviations are calculated from the sample, and the S1 square turns out to be 3.9. From the second team, another set of 8 wrestlers was selected randomly. Their average weights turned out to be 95 and S2 square is turning out to be 4. Now, if we want to test whether the second team has a higher average weight than the first team, then the question comes of which procedure to be adopted, because when the variances are unknown, we have 2 different procedures, rather 3 different procedures. Here of course, the 2 samples are independent, so the pairing is not required here, but the variances equality plays a role here. So, firstly let us test about, first we make a test for equality of variances. That means we test H naught sigma 1 square is equal to sigma 2 square against H 1 sigma 1 square is not equal to sigma 2 square. Now, here you see that S 2 square is bigger than S 1 square. So, we make F as S 2 square by S 1 square, which is equal to 1.026. Now, if we look at the F value on 9 degrees of freedom at say 0.05, then it is 3.1789. If we see F99 0.95, that is equal to 0.3146. So, you see here 1.026 is not greater than this value, it is not less than this value. So, H naught cannot be rejected. So, for testing about equality of means, we may use pooled sample variance procedure, that is SP square formula. So, if we apply that, we need to calculate SP square, that is here m minus 1 S1 square plus n minus 1 S2 square by m plus n minus 2. In this particular case, m and n are equal, therefore, this becomes simply S1 square plus S2 square by 2, that is equal to 3.95. So, the formula for the pooled test statistic here is square root of m n by m plus n x bar minus y bar by SP, that is square root 64 divided by 16, and this is minus 5 divided by 3.95, that value turns out to be minus 5.032. If we see here say T 14 at say 0.025 level, then it is 2.145, T 14 say 0.05, that is 1.761, etc. You can see here the calculated value of T statistic here is minus 5.032. If we are considering a test where our null and alternatives are given like mu 1 is greater than or equal to mu 2 against mu 1 less than mu 2, then here our rejection region will be J T is less than minus T m plus n minus 2 alpha. since minus 5 is smaller than minus 2 or minus 1, we will reject H naught. So, the average weights of the players in team 1 are smaller as compared to the second team. So, here we will say it is significantly smaller. If we had reversed this hypothesis, suppose I put mu 1 is less than or equal to mu 2 here and mu 1 greater than mu 2, then we cannot reject H naught. So, that means we are actually supporting mu 1 is less than or equal to mu 2 here, and of course, the hypothesis of equality is also rejected here. Therefore, we should say that mu 1 is greater than mu 2, because equality is also ruled out. So, actually this is what the point I wanted to emphasize, that when we write the hypothesis, then we should not simply get a conclusion based on one hypothesis and say something, rather than we should analyze the closely related hypothesis also. For example, in this case we are saying reject H naught. So, rejecting means mu 1 is less than mu 2. On the other hand, if we had framed it in the reverse way, then we cannot reject H naught, but then that would have meant mu 1 is less than or equal to mu 2, but actually equal to mu 2 is also rejected here. Therefore, we conclude that mu 1 is significantly smaller than mu 2 in this case. Let us consider, say, lives of certain electrical appliance, it is in hours. So, we have two brands of appliances, we want to compare the average lives here. For the first brand, 25 units were selected at random and put on the test, and their average lives were observed to be 380 hours with a sample variance of 100. For the second sample, 16 units were selected and their average were observed to be 370 hours, and the variances turn out to be 400. Maybe the second show has a smaller mean, less number of smaller average life, but the variability is more. Once again, if we want to compare the means, firstly let us compare the variances. So, first we compare the variances. So, if we take the ratio S2 square by S1 square, that is equal to 4. So, if we look at say f value on say 15, 24.05, that is equal to 2.1077. So, naturally if I am considering say the reverse of that, that is going to be smaller. So, H naught sigma 1 square is equal to sigma 2 square against H 1 sigma 1 square is not equal to sigma 2 square. So, here H naught is rejected, because if I consider f 24 15.95, that is going to be less than 1. So, naturally this is falling into this region, so H naught is rejected. So, we cannot pool sample variances. So, if we cannot pool, then we have to use that procedure which is given in the using Smith-Satterwhite procedure. So, we have the T star as x bar minus y bar divided by square root S1 square by m plus S2 square by n. So, that is equal to 380 minus 370 divided by square root of 100 divided by 25 plus 400 divided by 16. This value can be seen to be 1.857. Now, the calculated value of T star has to be compared with the T distribution on new degrees of freedom. Now, nu was given by S1 square by m plus S2 square by n whole square divided by S1 to the power 4 by m square into m minus 1 plus S2 to the power 4 by n square into n minus 1. So, after substitution of the values given here, we obtain this value to be 19.86. So, we will take T18. So, for example, at 0.05 level this value is 1.729. Suppose I consider 19, T19 at say 0.025, this is equal to 2.093 etc. You can easily see that the value 1.857, this is bigger than this but smaller than this. So, we can reject H naught. Suppose I am considering problem 1, okay, testing problem 1. So, in that case, suppose I am considering H naught mu 1 is equal to mu 2 against say H 1, mu 1 is not equal to mu 2. If I am considering this, then we can reject H naught at 10% level, but not at 5% level, because at 5% level T alpha by 2 value will be 0.025, that is 2.093, which is larger than this. However, if we are considering one sided test, that is H naught, say I am considering hypothesis testing problem 2. In the hypothesis testing problem 2, the rejection region is T star is greater than or equal to T nu alpha. So, at 5% level you will be rejecting, but at 0.25% level you will not be rejecting. Then we will be rejecting both at, then we reject both at 5% and 10% levels. However, if you consider say 0.025% level, then you will not be rejecting here. So, this test is slightly more sensitive here. Let us consider one example where the observations are paired. So, suppose we want to test the effectiveness of an exercise cum diet program. Okay. So, say 15 persons were selected, their weights are recorded before and after a 6-month training program. So, we want to see whether the average weights have reduced. So, let us see the data is given in this form: person. So, we have persons 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Initial weight is taken to notice whether there is a significant difference later or not. The weights are 70, 80, 72, 76, 76, 76, 72, 78, 82, 64, 74, 92, 74, 68, 84. After the program is conducted, what is the weight then? 68, 72, 62, 70, 58, 66, 68, 52, 64, 72, 74, 60, 74, 72 and 74. We want to test, suppose I say mu1 and mu2. So, the mu1 is the average weight before and mu2 is the average weight after the training program. So, we may be interested to test whether mu1 is actually greater than mu2. That means, we can put this as a strong hypothesis in the alternative, which actually we want to test. So, mu1 is less than or equal to mu2 against mu1 is greater than mu2. So, if we consider here the differences di's 2, 8, 10, 6, 18, 10, 4, 26, 18, minus 8, 0, 32, 0, minus 4, 10. So, let us calculate d bar, that is 8.8, SD is equal to 10.98. So, here n is equal to 15. So, the value of the t statistic here is root n d bar by SD, that turns out to be 3.1. If we are considering t distribution on 14 degrees of freedom, then the values say 0.05, that is say 1.761, t14 at say 0.025, that is equal to 2.145, etc. You can see that this value is significantly higher than these values. So, the hypothesis h naught mu is equal to 0 against mu d greater than 0. So, h naught is rejected. That means, we conclude that exercise program is effective. So, the training is effective. We are concluding that there is a significant reduction in the weight after the 6-month training program. We also have the normal test when we are comparing the proportions of the two binomial populations. So, for example, the data is recorded not in the numerical measure, but in the characteristic form. For example, we want to see certain opinions, we want to see the effect of certain say learning procedure. So, that may be the result may be in the form of that a test is conducted. So, for example, a set of students is taught a certain instructional material, another set of students is taught another instructional material, a common test is conducted. We want to see how many passed in the first set and how many passed in the second. Is there a significant difference in the proportions? That means, we want to see whether the instructional material 1 is better or the instructional material 2 is better. So, basically the situation is of the following form: testing for equality of proportions. So, the general model is of the form x follows say binomial m p1 and y follows binomial n p2. We assume these two samples to be independently taken here. So, we are interested in testing a hypothesis of the form p1 is equal to p2 against say p1 is not equal to p2, say this is 1. We may test p1 is less than or equal to p2 against p1 is greater than p2, or say h naught p1 is greater than or equal to p2 against h1 p1 is less than p2, etc. A large sample approximation can be used based on normal approximation to binomial. So, we may calculate here p as had x plus y by m plus n, p1 head is equal to x by m, p2 head is equal to y by m. So, this is the first proportion, this is the second proportion, sample proportion, this is the pooled proportion. So, we construct a statistic z as p1 head minus p2 head divided by square root p head into 1 minus p head 1 by m plus 1 by n, which is actually equal to root of m n by m plus n, p1 head minus p2 head divided by root p head into 1 minus p head. Under the assumption that p1 is equal to p2, z is approximately normal 0 1 for m and n large. So, we may make a test based on this. For 1, reject h naught if modulus z is greater than or equal to z alpha by 2. For 2, it will be reject h naught if z is greater than or equal to z alpha. For 3, reject h naught if z is less than or equal to minus z alpha. So, this is an approximate test. If the assumption that m and n are large is not true, in that case we may have to go for a exact procedure, but that procedure will make use of the distribution which is calculated from the binomial. So, under p1 equal to p2, the distribution of x plus y is again binomial, and one can make use of the distribution of x given x plus y, which is hypergeometric, and there is a test procedure for that, but we are not going to discuss that in this particular course here. Let me give an application of this here. Suppose one wants to compare the effectiveness of treatments by two different surgical procedures for a certain disease. So, for this a set of patients is taken. On one set of patients, one surgical procedure is adopted, and we observe the proportion of success. So, let us make the data in this particular fashion. Suppose 100 patients are there on which treatment procedure 1 is adopted. We see how many are successfully treated and how many of them are failures. Suppose in out of 100 here, it turns out that 63 are successfully treated, 37 are unsuccessful. Whereas using the treatment procedure 2, suppose 150 patients were given this procedure, out of that 107 were successfully treated and 43 are not successfully treated. That means, on them the surgical procedure did not yield any positive result. Let us look at the proportions here. P1 head is 0.63, P2 head is equal to 0.71 and P head is equal to 0.68. So, if we calculate the Z statistic here, that is P1 head minus P2 head divided by root of P head into 1 minus P head into root mn by m plus n, this value turns out to be minus 1.33. If we are considering any reasonable level of significance, say Z 0.05, that is 1.645, suppose I take Z 0.01, that is 2.32, etc., then you can see that if we consider, say, hypothesis H naught P1 is equal to P2 against, say, H1 P1 is not equal to P2, then at level of significance, say 10%, 2%, etc., H naught cannot be rejected, because the absolute value of Z, that is 1.33, is smaller than these values. So that means there is no significant difference in the success rate of the two surgical procedures. So, no significant difference in the success rates of two procedures. Although from here it looks that the second procedure is more effective, but statistically speaking there is no significant difference here. We have seen here that sometimes the assumption of the correlated observations is required, as in the case of exercise program, etc. But we have seen the use of paired t-test should be done under certain checks. That means, we should use it with care. For example, we are adopting a paired t-test procedure, but the value of the correlation is, say, 0. In that case, sigma 1 square plus sigma 2 square will be the variance of xi minus yi. That means, we have unnecessarily reduced our degrees of freedom. Here we are using only n minus 1 degrees of freedom. Consequently, our power of the test will reduce. So, it is not advisable to go for a pair t-test here. That means, in such a case it will be a reasonable option firstly to check whether the correlation is 0 or not in the given data set. So, fortunately, we can find actually a test for the correlation coefficient being significantly different from 0 or not. So, testing for correlation coefficient. So, we have the data x1, x2, xn, y1, y2, yn. So, in the two data sets, we consider the sample correlation coefficient and the population correlation coefficient. Suppose the theoretical correlation between x and y variables is rho. So, we want to test whether rho is equal to 0 against say rho is not equal to 0. So, for this we calculate the sample correlation coefficient, that is R, that is equal to Sxy divided by Sx where this Sx square is 1 by n minus 1 sigma xi minus x bar whole square, Sy square is 1 by n minus 1 sigma yj minus y bar whole square, and Sxy is equal to 1 by n minus 1 sigma xi minus x bar into yi minus y bar. That is the sample standard sample variances for the two samples, and this is the sample covariance. So, based on this we define the Karl Pearson sample correlation coefficient. Then it has been observed that square root n minus 2 into r divided by root 1 minus r square, this is having a t distribution on n minus 2 degrees of freedom when rho is equal to 0. Let me call it t star. So, one can make use of this for testing the significance of correlation, that means whether there is a significant correlation between the two variables or not. Let us consider one example here. Suppose the data on incomes of parents and children, their children is available. It is assumed that there is no significant correlation between the average incomes of parents and their children. So, 43 pairs are selected and their sample correlation was calculated, which turned out to be 0.412. So, from here this t star value, that is square root 41 into 0.412 divided by square root 1 minus 0.412 square is calculated. This value turns out to be 2.9. Suppose we are considering say t on say 0.005 at 41, this value is 2.7. Now, you can see here that this is extremely small level of significance we are taking. So, H naught is rejected at any reasonable level of significance. This is actually 1% level. So, at 1% level itself this is rejected. That means the incomes of children are related to the parents. That means higher income parents, their children will also tend to earn higher incomes, and lower income parents, their children will have lower incomes here. Now, this test is again based on the normality assumption. Sometimes the normality assumption may not be valid. In that case, there is a large sample test for correlation coefficient. when n is large and say rho is equal to rho naught. So, we may not test that rho is equal to 0, but some arbitrary value rho naught, then we construct z that is equal to root n minus 3 by 2 log of 1 plus r divided by 1 minus r minus log 1 plus rho naught divided by 1 minus rho naught. Then this has approximately normal 0 1 distribution. So, consequently, if n is large, then we may test about the correlation being equal to any arbitrary value. Of course, if rho naught is 0 here, then this term will vanish and we will have only this particular term. So, this is an approximate normal test here, and this is not based on the assumption of normality for the initial samples, that is x i's and y i's here. Let us take a few more examples here of the tests that we have discussed today. So, let us take one example based on say normal distributions here. The following random samples are measurements of the heat producing capacity in millions of calories per ton of a specimen of coal from 2 mines. So, in mine 1 there will be 5 measurements are taken, the values are 8260, 8130, 8350, 8070, 8340. In the mine 2, 6 observations were taken, 7950, 7890, 7900, 8140, 7920 and 7840. Test whether the difference between the two means is significant. So, here 2 samples are available to us, and we are having 5 and 6 observations respectively from the 2 samples. So, what we do here, we have to check whether mu 1 is equal to mu 2 or mu 1 is not equal to mu 2. But once again here, to test this hypothesis, we will have to test about the variances also. So, whether the variances are same. So, here we see that if we consider S1 square here, S1 square is equal to 15,750 etc. S2 square is equal to 10,920. So, if we consider the ratio here S1 square by S2 square, that is approximately 1.5. So, if I am looking at the F value on say 1, 2, 3, 4, 5, so 4 and 5 degrees of freedom, let us see one example here from the tables of the F distribution, and say at 0.05 level, if we are seeing F45, so at 0.05 the value is 5.1922. So H naught sigma 1 square is equal to sigma 2 square cannot be rejected. Now, if this cannot be rejected, then for the equality of means we will go for the pooled sample variance procedure. So for testing equality of means, we will use pooled sample variance procedure. So, if you see SP square, that is equal to 4 S1 square plus 5 S2 square by 9, that turns out to be, so that is equal to, well, that is a huge value here, 4 into 1 15,750 plus 5 into 10,920 by 9. So, that is equal to some value. So, SP is taken to be square root of that, that is 114.31. So, if we calculate the t variable here, that is root mn by m plus n x bar minus y bar by SP, then first thing is we observe here that x bar is equal to 8230 and y bar is equal to 7940. So, this value turns out to be, after calculation, 4.19. So, if we see the t values at say 9 degrees of freedom, then even at 0.005 this value is 3.25. So, at 1% level also the hypothesis of equality of means is rejected. So, we conclude that in the two mines the measurements of the heat producing capacity are significantly different, because it may be due to difference in the type of the coal that is available, it may be due to the type of the mine that you are having. Maybe in one of the mines you have a very low level roofs and various kind of parameters which may be operating in those mines there. So, it may be due to that. So, to sum up, if we are comparing the means of two normal populations, the first thing is we have to look at is that what type of variances are there. If the variances are known, then we have one type of procedure. If the variances are unknown, then we firstly test whether the variances are same or not. If they are same, then we go for a pooled sample variance procedure. If they are not same, then we go for a different procedure, which is an approximate test. We also see the correlation. If the correlation is present, then we may go for a pairing. If we do not have the correlation, then we may go for independent samples. So, before adopting any procedure, one has to carefully examine the problem and then choose the appropriate test. We have also seen the effect of choosing the null and alternative hypothesis. As I have already mentioned, since we are controlling the probability of type 1 error, therefore, it is always reasonable to put the stronger hypothesis, or you can say the conviction in which we have more, that hypothesis as an alternative hypothesis, because rejection of the hypothesis is a strong conclusion, whereas acceptance of the hypothesis becomes a weaker conclusion, simply because of the reason that we are actually controlling the probability of type 1 error. In the forthcoming lecture, I will be discussing the chi-square test for goodness of fit or testing for the independence.